I'll talk to you today about gravitational waves. I've given it a subheading of stretching the limits, which is just because of the way gravitational waves work. They're stretching and squeezing of space and time, or space-time. And also, we're right at the limit of what we can do with physics with these things. So let me start off, and I want to start off by going back and looking at some history. So here's someone you may have seen or heard of before. This is a chap called Johannes Kepler. He is an astronomer who was around at the end of the 16th century, start of the 17th century. And he came up with something called Kepler's laws of planetary motion. And he established that the planets don't move in circles, they move in ellipses. He made a relationship between how long it takes them to go around, so the period of their orbit, and the size of their orbit, the radius or the semi-major axis, to give it its proper name, of their orbit around the sun. So this was a while ago, but he was not working in isolation. He produced this thing called Astronomia Nova. A lot of stuff was written in Latin back then, at the turn of the 17th century, so 1609. And this was on the way these things work. And you might be able to see on the screen, it might not be big enough, but you can see Copernicus here. So Copernicus was another person, Ptolemy, Tycho Brahe. So he was building these. These are all people. These are all other astronomers. And in fact, he was definitely not working in a vacuum. He was building on the work of a few people you may have heard of. So Nicholas Copernicus, you may have heard of the Copernican revolution. Sorry, Copernicus was the person who really first proposed a heliocentric model, from the sun at the center. So that's the idea that the planets go around the sun rather than the sun and all the other planets going around the Earth, which was a favored theory at the time. At about the same time, or sorry, a little bit later than that. So he came a bit before Kepler and these other two people. So Tycho Brahe was a Danish astronomer. Copernicus was Polish. Galileo was an Italian astronomer. He's very famous, of course. He was trying to understand the nature of gravity, and he did possibly apocryphal tales of dropping things off the Tower of Pisa, where he established that two things of different masses fell with the same acceleration. But that experiment of showing that if you drop two things under gravity, they fall with the same acceleration. So if I drop a brick and a marble, they'll both accelerate at the same rate and hit the ground if you ignore air resistance and so on. That's an experiment that was redone on the moon with I think a feather and a hammer in one of the Apollo missions. So Galileo was trying to understand the nature of gravity. Tycho Brahe was a very, very careful observer, and he was before the telescopic age, before Galileo and others had first started observing the skies with telescopes and first developed them. So Tycho Brahe was a very careful observer using the naked eye and was mapping the stars and the planets, and that enabled those observations. And Kepler was his student to really map these things out and understand what gravity was, or what the motions of planets were doing. It wasn't yet linked to this one theory of gravity. Let's jump forward. So that was the start of the 16th century. Let's jump forward towards the end of the 16th century. And this person here, Isaac Newton, you've probably heard of Isaac Newton, I hope. With his famous Newton's laws of motion. And his big publication was a company called Principia Mathematica. Mathematical principles of natural philosophy. And this was where he came up with something called the Newtonian law of gravity, which we'll touch on in a second. So he gave us Newton's laws and lots of other things as well. But also, he was not working alone. He was not working in isolation. So you can see a few other people who are around at about the same time. These are all roughly contemporaries. So Robert Hooke, of Hooke's law fame. So if you've done anything with springs and extending springs, you'll use Hooke's law. So he determined that gravity seemed to be this attractive force pulling things together. And that he also determined it was an inverse square law. So that means as you get twice as far away, if you get twice as close, it gets 4 times stronger. If you get twice as far away, it's 4 times weaker. So the square of the distance. He didn't call it an inverse square law. In the wonderful language of science back then, he said attraction always is in a duplicate proportion, squared, to the distance from the center reciprocal. So the distance from the center. So they used very flowery language back then. At about the same time, Halley, of Halley's Comet fame, was also making observations. He was a bit of a polymath. He did worked in lots of different things, and he invented a diving bell, which lets you go underwater with a pocket of air. Well, he's first to use it, maybe. And he was having a discussion with Hooke and Newton about gravity and its very nature. And then Christopher Wren, who really was a polymath, that's someone who studies lots of subjects. He was an architect primarily, is what he's mostly remembered for. But he set a challenge to initially to Halley and Hooke to explain planetary motion using a universal law. And this is where they started conversations with Newton, who it turns out had also been working on this. And they came up with the idea, or Newton came up with the Newtonian gravity, so building on all this work. Now, I'm not sure exactly how many of you are in which year. So some of you may have done Newton's law of gravity, and some of you may not in your A-level studies. But I won't be testing on this at the end. I would say there won't be an exam on this, but if you do A-level physics, there might be an exam on this at some point. So the idea of Newtonian gravity was that if you get two masses, I'm going to call them big M and little m for short, and you separate them by distance r, what Newton showed is that you could calculate the force between those objects. And he said it's proportional to the product of the masses divided by the square of the distance. That's that inverse square law. So if you've not seen this before in your studies, then don't worry. If you have seen this, then it'll be familiar to you. Now, this is a very simple universe, if you like. It's just got two masses separated by distance. You could extrapolate, you could make this more complicated if you want, but it gets more and more difficult to solve. There's a famous thing in astronomy with physics called the three-body problem. If you add a third body, the equations get very, very difficult to solve accurately. So what's this telling us? Well, the thing on the right, the masses, how big the masses are, how massive those objects are, and how far apart they are, it's kind of telling us where matter is, where stuff is in this very simple universe. And the thing on the left, the force, is telling us how matter moves, because one of Newton's laws, his second law, is that if you have a force, then you create an acceleration on an object. So F equals ma being his law. So he then determines that if you know where matter is, you can determine how matter is going to move using Newton's law. And we can try and put in some numbers. So let's try and look at the force that would be between me and the Earth, or a person, the Earth. We don't have to personalize this too much. So let's do some nice rounding. So the mass of the Earth, big M, I'm going to call it, I'll give that big M rather than little m, is 6 times 10 to the 24 kilograms. The mass of a person, rounded to the nearest 100 kilograms, is 100 kilograms. And then the distance from the center of that object, of the Earth, is about 6,000 kilometers, so 6 million meters. It's a little bit more than that, but we're just doing a rough calculation here. So if we put those numbers into this equation, then we get mm over r squared we put these numbers in, so 6 times 10 to the 24 times the 100 to the little m divided by the 6 times 10 to the 6 squared, and so on. You get a number that's 1/6, don't worry too much about that, times 10 to the 14. So that's a very, very big number. And yet I know the force on me isn't horrendously strong because I can overcome it. I could jump up on my chair and I can overcome the force of gravity, and all that is my legs. My legs are a lot smaller than the Earth. So my legs can cause me to accelerate, even given this enormous quantity here, mass 1 times mass 2 divided by the distance squared. And the reason for that is that Newton's law of gravity has this constant, Newton's gravitational constant, or big G to its friends, out of the front. So this is the constant of proportionality in this equation. And the reason we can overcome gravity is because when you use SI units, kilograms and meters and seconds and so on, this number is very, very, very small. It's 6.67 times 10 to the minus 11 newtons per kilogram per meter squared. So it's a very, very small number. Gravity is very, very weak compared to things like electrostatic forces. The reason I'm not currently plummeting through my chair and through the floor is the electrostatic repulsion between my feet and the floor is overcoming the entire pull of gravity of the entire planet Earth. So that was Newtonian gravity, and it works really, really well. We use Newtonian gravity to travel around the solar system. We send spacecraft flying around to other planets using Newtonian gravity. We don't really have to go much further. And certainly all the experiments you do in school, if you're doing experiments in school that disobey the laws of Newtonian gravity, you're probably doing the experiment wrong. At least I hope you are. Otherwise, you've invoked relativity in the school classroom. And that's a dangerous thing to try and do. So let's move forward from Newtonian gravity, which works very well and which we study in school and at university in a great length. and so on. Let's jump forward to the turn of the 20th century. And this chap, someone else I'm sure you've heard of, Albert Einstein. So he was around in 1879, born in 1879, and he was doing a lot of work in the early 20th century. He did three big things. One was the photoelectric effect, which you may hear about at some later stage. I won't go into that now. He also did some studies in 1905. He published his special theory of relativity, and that was saying if things are moving really, really quickly compared to the speed of light, which he proposed was a constant in the universe, a very fast constant, but a constant nevertheless, you couldn't break it, then objects would experience time and space in different ways. This also came up with this famous theory, E equals mc squared, which is one of, if not the most famous equation in science, I guess. But then, so that was 1905, and he'd established that the speed of light was a constant, so on. So what that meant, we know the speed of light is a constant. It takes 8 minutes for light to get from the sun to the planet Earth. So if some presumably malevolent alien race went and turned the sun out and made it stop shining, it would take us 8 minutes to realize that. So that's something that we know of in physics. But his question was, well, what about if some alien race came and plucked the sun out of existence and made its gravitational pull disappear? At what point would the Earth, instead of going around in a circle because of the gravitational attraction, at what point would it move at a tangent and just go in a straight line? Would that be immediately? Would it be after 8 minutes? Would it be next Tuesday? When would this happen? And he determined, he was trying to solve that. He was also trying to figure out what happened if you experience a gravitational pull, if you're in a gravitational field and you move really quickly, what happens then? And so he came up with this theory of general relativity in 1915, published in German back then. And he, again, like all those people before, was not working in isolation. So these people were in, I guess, order from bottom to top, really. So Riemann was a mathematician, and he came up with some of the really basic math that's so critical to general relativity. He came up with the idea of tensors. So if you're doing A-level maths, you may, or further maths maybe, you may have come across matrices, which is this idea of representing sort of grids of numbers and so on. They're really useful in physics. And a tensor is basically a matrix that's got a physical purpose. It's got a physical reason for being. It's got physical importance, physical meaning. Based on some of his work, Hermann Minkowski was actually Einstein's supervisor, his boss essentially. And Minkowski came out with this idea of taking space and time and making them, instead of 3 dimensions of space and 1 dimension of time, of thinking them as 4 dimensions of space-time. So it was Minkowski who came up with space-time as a concept, which is something you may have heard about. And then Hilbert was really Einstein's contemporary. He was around at the same time, and he was again another pure mathematician. And he developed something called field equations, which is where you take the matrices and the tensors that Riemann had done, this maths that he developed. You apply it to 4-dimensional space-time, and then you can start doing some physics with it. And Einstein was building on that as well and came up with this idea of general relativity. Now, I'm not going to go into the details of what general relativity is. It's a very complex field. You can touch on it. We can touch about basic things. But the idea was, what Einstein said is, instead of thinking of these things as a force of gravity, he said consider space-time to be this deformable medium. So to create analogies to this, we often have to, we're trying to look at 4-dimensional space-time. That's hard enough. But even looking at 3 dimensions of space and trying to imagine warping that, it's hard to visualize 3 dimensions. So what we tend to do is compress everything down to 2 dimensions. So there's a graphic here showing that green grid is the universe, is space-time. Another way of looking at this is to say, let's imagine space-time as the surfaces of a trampoline. And that can be stretched and deformed. And the easiest way to imagine deforming a trampoline is to make it move up and down. And so let's take a trampoline. And if I rolled a marble across a trampoline, it would move in a nice straight line. I presume the trampoline was flat. But let's go and do something different. Let's go and put a massive object in the middle of a trampoline. Let's go and put a bowling ball in the middle of the trampoline, or get my 4-year-old to sit still in the middle of the trampoline. Well, what that'll do is it'll deform the trampoline and make it bend downwards. Now, in terms of an ant walking across that trampoline, it might not notice the fact it was bending downwards, but it would notice that things were a bit distorted. And now if I tried to roll a marble across the trampoline, it wouldn't move in a straight line. If it got close to the bowling ball, or my 4-year-old, it would go in a curve. And if I got the speed just right, it might go in a circle. And Einstein's equation said, if you imagine space-time being distorted in such a way, then actually you come up with the same, pretty much the same effect that Newtonian gravity has. And it's got this idea of space and time being distorted. So when you're in a gravitational field, it's just that space-time is stretched a little bit. And so things like time move differently, and space move differently. And that's what causes things to move in circular orbits. That's why you get things moving in orbits, and why you get things falling towards each other. If I put a marble on the trampoline a little way away, it would just fall towards the bowling ball. Now, this sounds all well and good. Does it make any firm predictions? Well, actually, it does. So here's another visualization of the Earth in a gravitational field. And off to the left there is a satellite. And this is a not to scale, or very much not to scale representation of a GPS satellite. So if I'd come to visit you in your school today, I'd have probably used this thing here to travel there, sat nav. And that would have been talking to GPS satellites. Those GPS satellites are 20,000 kilometers away from the Earth. They're a long way up. And the field of gravity, the gravitational pull from the Earth, is weaker 20,000 kilometers away because of that inverse square law, essentially. And because if you look at this graphic here, the near the Earth, the space is distorted more than it is far away from the Earth. So there's a couple of effects from being in orbit. One is those satellites are moving pretty quickly around the Earth. Orbital speed around the Earth is, tens of thousands of miles an hour. And actually special relativity comes into play, because actually means that going at that speed, time moves slightly slower. So about 7 microseconds a day slower. But because the gravitational field is weaker, then actually time moves, that general relativistic effect from being a gravitational field makes time move faster. So 45 microseconds a day faster. So those two partly cancels out. It cancels out the special relativity and then some more. Time up there in space, 20,000 kilometers away, moves faster by about 37, 38 microseconds a day. Now, 38 microseconds in one day isn't very much, but GPS is all about very careful timing of signals from satellites. And so it has to be corrected for, otherwise we'd all get lost very, very quickly. And so the satellites up there that have atomic clocks that are tuned, that's the little atomic vibrations vibrating very, very regularly, they are tuned ever so slightly differently from an atomic clock here on Earth, just to counteract that effect, or counter that. So what was Einstein's theory? Instead of this equation here, which is Newton's theory, he generated something called this is the field equations. It looks like a fairly simple equation. It's got a G in it still. What is it telling us? There definitely isn't an exam on this in any A-level study, don't worry. But this thing on the right is called the stress energy tensor. And that's actually a tensor. It's a matrix that says where stuff is in the universe. Where is matter? How much matter is in the different places? Maybe how is it moving? Maybe is there energy as well? If there's stuff that's got various bits of energy and so on associated with it. You might have heard of things like dark energy and so on. That's where that all comes into play. And then the thing on the left is how space bends. And if we know how space bends, how that trampoline analogy is being distorted, then that tells us how matter is going to move. So it's doing what Newton's laws did before. Now, if space is bending, it can't be that noticeable. If I go walk past a very big building or past a mountain range or something, I don't suddenly notice that space is sort of being distorted and my watch is ticking slow or anything like that. This sounds like must be a very, very small effect. And the reason is that number out the front, that constant proportionality. So we have here 8 pi. You can sort of ignore the 8 pi. That's nothing in the grand scheme of things. But G, which we established is Newton's gravitational constant, is a very, very small number, 10 to the minus 11. This thing on the bottom, c to the power 4, that's the speed of light to the power 4. So that's speed of light is 300,000 kilometers a second, so 3 times 10 to the 8 meters per second in SI units. So 3 times 10 to the 8 to the power 4. That's a very big number to the power 4, which is an incredibly large number. So what you have here is just a very small number divided by an incredibly large number, and you come out with a tremendously small number when you start to run out of superlatives. And if you take g divided by c to the power 4, you get something that is along the lines of 10 to the minus 44, right? And I probably don't need me to write that out, but it can write out there. I could write out all the zeros. It would take a long time, so let's just skip ahead. That's what 10 to the minus 44 looks like. It is an incredibly small number. So there's 44 zeros there. And that's because space-time is really hard to deform. So to make anything that is noticeable, you need things that are very, very massive. And actually, you need them to be moving. Well, you need them to be very massive. So notice any changes in that distortion need to be moving very, very quickly. Now, let's go back to this analogy here. How I just said it's very hard to stretch. That constant g over c to the 4 is very small. How stretchy is it? If you can apply a force, apply a stress to something, and then cause it to stretch, to have a strain, then you can actually think about the elastic modulus. And you may have done this experiment in school. So here's a table of some elastic moduli of some common materials. The units are in gigapascals. Don't worry too much about the absolute units. These are rough numbers. The elastic modulus of rubber is 0.1. Pretty easy to stretch rubber. Wood is 10. Concrete, actually not that much stronger than wood. Steel, much stronger. That's why we build buildings out of steel a lot often. And then diamond is the toughest material we know, elastic modulus of 1200. So if we were to do that same calculation for space-time, in terms of the amount of stress, the amount of force, if you like, you need to apply to make it stretch, what's the number for space-time? What is that? It's 10 to the power 24. So that's a million, which is quite a lot more than anything we know. So space is hard to stretch. So if you want to stretch it, you need to have things very massive. Now, what are the most massive things we know of in the universe? Well, we think of black holes, stars, black holes, that kind of thing. And if you want things to be changing, you want them to be moving really, really quickly. And if they start moving quickly, then you can notice some changing effects. Now, how do you get things to be moving quickly? In astronomy, in space, they end up going around. If they pass by, they'll pass by each other. You get a brief effect, and then it'll stop. But if they're orbiting each other, then that can continue for a long time. And you get an interesting effect. So let's go back to our analogy. And here's a test done by someone called Steve Mould. And this is a latex or rubber sheet, a stretchy sheet that he's got pinned down just the right pressure to simply make the simulation to a big hula hoop type thing. And he's going to spin something in the middle. So he's actually got a power drill. I'm not sure you can hear the audio. It doesn't matter. He's got a power drill with 2 castles on it. And he's going to spin them round. You saw that effect. So if we look at what happens in slow motion, he does a time-lapse photography of it, then that's what you see. These things going around are causing that space-time. This is the same effect if I got 2 bowling balls on a trampoline and made them move in circles around each other. This is the kind of effect you'd see. You get these ripples, these spirals traveling outwards. And those ripples are representing space-time being stretched and squeezed, distorted in different ways. And we can do that on a real simulation of black holes as well. So here's a simulation of black holes. Pause it a second. So this is a simulation of 2 black holes, the black things in the middle. And the color scheme is how much they are distorting as they go around each other. These ripples in space and these things moving around are causing space to be distorted. Now, as these waves are traveling away, the whole system is losing energy. What that means is these things spiral in towards each other and they get closer together. And eventually they're going to merge into one big black hole. And so they go around each other, they emit these waves. You can see the distortions are getting a bit bigger. And then eventually they touch, their event horizons merge, and they form one big black hole that then just sits there spinning on its axis in a big ripple of gravitational waves. So that was a real computer simulation of black holes done solving Einstein's laws of gravity. So it'd be really great to be able to go and test these things. Now, what do they look like when they pass by? So I showed those ripples going out, these ripples in the fabric of space-time. Well, that's all very well, but what does a ripple in space-time look like? Well, if you imagine a ripple in space-time traveling through the screen, so through the screen that you're looking at and through your classroom, I can see a few of you off the side. I'm going to try and do this experiment. Let me see if I need to get myself on camera a lot so everyone can see. So what I'd like you to do, I'd like you to join in this experiment, is can you all stick an arm in the air for me? There we go. Thank you. I can see you. Right. That's one arm in the air. And I want another arm out to the side. You can just about see me. There we go. Right. So you should have an L shape of arms. Now, the gravitational wave passes through the screen and through your classroom now from front to back or back to front. If you got a crest of that wave, it would stretch up and down and it would squeeze side to side. So stretch the up arm up and pull the side one in a bit. So you can see me. And then if you get to the top of the wave, it does the opposite. It stretches the side one out and it pulls the top one down. It's a wave, it oscillates. So it goes up and in and then out and down. And it'll be stretching up and squeezing in and then squeezing out and stretching and stretching sideways and squeezing up and down. And so it'll oscillate and all this. And if you wanted, you could do your yoga exercises in the morning to the pattern of gravitational waves. So that's what a gravitational wave would do. If it passed through, it would cause things to stretch and squeeze. Albeit you not at a particularly noticeable effect because it's so weak. Now we can go and try and detect those. And in fact, we do try and detect them. We detect them with gravitational wave detectors or observatories distributed all around the world. There are two in the United States called LIGO Hanford and LIGO Livingston. They're currently operating. I had the good fortune to go and visit Hanford earlier in the summer. GEO 600 is a sort of a test bed instrument in Germany. It's a British-German collaboration. Virgo is an Italian European detector with a lot of French and Italian involvement, as well as the rest of Europe as well. That's in Italy, just outside Pisa. CAGRA is a detector underground in Japan. And then LIGO India is a LIGO instrument being built at the moment in, unsurprisingly, India. So there are 5 working. One of them's a test bed, as I said, and there's another one being built. Now, you don't do these. It's not just in Cardiff. I think we're the 4th biggest group in the world doing this, but we are by no means the only ones. Here is a map of all the institutions involved in LIGO, the LIGO Scientific Collaboration. That's an awful lot of institutions. There are something like 2,000 people involved in that. And here, if you just look at Europe, is the Virgo collaboration. So you can see those blue dots are the LIGO institutions and the red dots are the Virgo institutions. And then we have CAGRA now as well to add to the mix over in East Asia. So it's a lot of people, thousands of people working together to do this. If you want to see a few of those people, then you can go to Humans of LIGO. Is a website that just showcases a few of the people involved and what they enjoy and what they're doing and how they got into it and so on. So I do recommend checking out humansofligo.blogspot.com or just Google Humans of LIGO. It should come up. So what do these detectors look like? Here's some pictures of them. So you remember I got you doing that L shape with your arms. Well, here are these detectors and they're all L-shaped. So if we look at LIGO Hanford, got some buildings here. It's got an arm stretching up into the distance towards that mountain. The mountain in the back is called the Rattlesnake Mountain. So this is Washington State in the United States. And then it's got another arm that's coming out to the right off the edge of the photo. Livingston is the same, one out through the swamps of Louisiana, and then another one off to the side. Virgo just outside Pisa, you can see as well. And the GEO is alongside some farmers' fields in Germany. And then CAGRA is underground. Now, these things you might be able to tell are pretty big. You might just be able to see some cars in this Hanford photo and the Livingston photo. These arms stretch for 4 kilometers. So I think there's 4 kilometers into the distance. Now, why does it have to be so far? Well, because of the way these operate. So what these do is they have a laser in this central building. The laser is pretty powerful. It gets split into 2, and one half goes up this arm, up the arm going up in this photo, and the other half goes along the arm, the arm going off to the side. It gets the ends, it reflects off mirrors and comes back again. It's something called a Michelson interferometer or Michelson interferometer. And when it gets back and they get recombined, then they should be exactly in phase. They should have traveled the same distance. It's set up to travel the same distance. And actually, when they get back, there's a bit of there is actually a phase shift that goes on. So they get back and they should cancel each other out. I'm not sure whether the animation is showing a real rate on your screen. That's an animation of some red lines. But we look at it in the terms of the waves. These lines get split into 2, the blue and the yellow. They're all the same color. They're colors just for graphical representation. Reflects off a mirror, slightly non-physical representation of reflection there. Travels to the beam splitter, And as I say, it's set up so it's exactly out of phase. And that means they will cancel each other out. But if one of those mirrors has moved, if space has got stretched, that phase shift will change. And if they shift so they're slightly in phase, you'll get a little bit of light appearing on your detector. And that's the kind of effect that's being looked for, that tiny shift in phase. And this is a greatly exaggerated effect on this animation. So how big an effect are we looking for? Well, let's zoom in to the kind of size we're able to detect with LIGO, Virgo, and CAGRA. So here is an image that's about 1 kilometer across or thereabouts. That's LIGO Hanford as it happens, but let's zoom in by a factor of 1,000. So we've zoomed into something that's the vacuum chambers. These lasers travel along a vacuum tube. That vacuum tube is about 1 meter wide. This tube you can see pointing off to the side. Let's zoom in by a factor of 10. And we get to one of the mirrors. You can see some people, and then a mirror that's a few tens of centimeters across. I think about 40 centimeters across. Made of, they're $250,000 each. They are the most expensive, most perfect mirrors ever made by a company in Germany. Let's zoom in by a factor of 100 million or thereabouts, and look at an electron microscope image of a mirror. Mirrors are made of glass. That's a silicon dioxide. Someone has kindly in the bottom half of this picture colored in the silicon green and the oxygen red. You can see that's the atoms in that mirror. So we've zoomed in to a scale of about a nanometer across for a few of these atoms. We've zoomed in from where we started by a factor of 1 trillion by now. Okay, let's go in by another factor to one of those atoms. We zoom by another factor of 100, and we get to 1 atom. Okay, so we've got 1 atom there. This is obviously a cartoon of an atom. I'm not quite sure why in this the electrons are all different colors, but it's not really very physical, because in actual fact, if you were to try and do this cartoon to scale, it would look like that, because you can't see the nucleus compared to the size of the atom. The nucleus is 10,000 times smaller than the atom. So there's what's a Wikipedia picture of a nucleus. With its protons and neutrons. The protons are red, the neutrons are blue in this picture. I don't know what color they are really. They don't really have a color. But let's zoom in. So we zoom in now by another factor of 10 into that one of those protons. We zoomed in by a factor from where we started of 1 quintillion. So that's 10 to the 3, 6, 9, 12, 15, 10 to the 18 we've zoomed in so far. We're going to zoom in again by another factor of 10, and again by another factor of 10. And then finally, we're going to zoom in one final level. We've zoomed in by 10 to the power 21. That's 1/60th of where we started. Right? We're looking at a scale of 0.001 femtometers. Is 1,000th the diameter of a proton. And a distance change of that 1,000th diameter of a proton from where we started with a kilometer, of order a kilometer long arm. It's the kind of change in length that these detectors can measure. Now, that sounds absolutely absurd. That sounds completely unachievable. There are all sorts of things that would stop that working. The ground moving, the tides, even waves hitting the ocean floor. The ground moves about a micron each way. And we're here talking about fractions of a femtometer. Thermal variations, these things will expand as they heat and cool. There will also be thermal variations. These things are not at absolute zero. These things are just the molecules are vibrating ever so slightly by way more than you can see there. They're scattering. The laser beam travels along a vacuum, but there'll be little bits of air. We can never make a perfect vacuum. The laser might get scattered off bits of oxygen or bits of air or whatever that are left in there. There's quantum noise. You try and make a laser. A laser does not emit a photon every second or every fraction of a second regularly. It emits them at random intervals. And so you get random noise associated with that. And then finally, the laser, you're trying to measure the brightness of this laser. The laser brightness might be varying over time unless it's perfectly stable. We're going to take into account all of these things. Now, I don't have to go into time. I don't have time to go into the way they've done this, but they have several ways of counteracting, for example, the motion of the ground. So you can see in this middle picture, this blue frame with some big springs on. That's an active suspension. So as the ground moves right, it moves left. As the ground moves up, it moves down. And so it can take into account things like the effect of the tides. The tides from the moon also make the ground move around. So you can take that into account. and very slow variations up to maybe 10 hertz, a few tens of hertz. It can take into account there. To damp out the very high frequencies, it uses a quadruple suspension. You can see it drawn on the left here with some masses, and these are some mirrors. It actually has two pairs of mirrors, and these mirrors are then suspended, and that suspension, that pendulum, quadruple pendulum, four one on top of the other, damps out very high frequency motion. And you can see that if you try and have a pendulum and try and move it really quickly, it doesn't. If you move the top really quickly, the bottom won't move very much at all. If you move it slowly, the bottom will move along. So you have this quadruple pendulum. There's an interesting thing here, actually, is that you're trying to measure things moving at 1,000th the diameter of a proton. What you can't do is go and prod it, because you can't move it that little. So what they do is they have another mass suspended behind it with an electric coil in it. And there's an electric coil in both of these things. They put a current through this electric coil, which induces a magnetic field, which induces a current in the other coil in the back of this front mirror. And then that pushes them apart by, so they use electrostatic repulsion just to push these mirrors apart by absolutely minuscule amounts to try and keep them stable. And you can see a picture of these in real life. You can see those bottom two stages of that suspension. There's more up above this as well. They also, this Michelson interferometer is not quite just a simple interferometer. It has an extra mirror, these partially silvered mirrors. Here's one of these $250,000 mirrors shown there on the right. The laser actually bounces backwards and forwards a few hundred times before coming out again, just to give it more time to essentially absorb the stretching of space-time or experience the stretching of space-time and so on, just to integrate, amplify the effect. So what effect do you get from all of this? Don't worry too much about the details on this plot, but this is showing how sensitive it is. How much is the noise in one of these plots? And here, the background noise, the lower, the better. This is showing against frequency of the effect it's trying to measure. So 10 hertz over here on the left, thousands of hertz here on the right. And the lowest frequency, the lowest noise you can see, which is the red line, is the total noise, is down here at about 100 or so hertz. So that's the kind of frequency it's looking for. And it can measure this displacement, this movement, at those kind of distances that we were talking about, and the different curves, the different contributions to this noise from different things, such as Brownian motion and thermal noise and seismic noise and so on. You can see this resonant peak here, this brown and green spike on the left. That's the resonant frequency of that pendulum system at about 10 hertz, and you see it peaks there, but then it drops off very, very quickly. So it's sensitive down at these frequencies about 100 hertz. The blue line is that quantum noise. You beat that if you make your laser more powerful. There's very few things that don't get better if you make a laser more powerful. Now, it sounds absolutely ludicrous, and it's been something that's been going on for decades to try and search for this. And then just as it was turning on back in 2015, this advanced LIGO phase, after the initial LIGO phase before that, that these signals came in. Now, the dark lines on here, the dark lines, these yellow, darker yellow and the darker blue lines, are the data measured by the two LIGO detectors which were running at the time. And the light yellow lines you might be able to see on the top are the predictions from relativity. And they match up. Right? They match up perfectly. So there was a signal from two black holes merging, two objects merging. They were spiraling around each other, spiraling in faster and faster. The next plot, this is the plot from the paper that was published. You can see the simulation, the red, and the grey here in the middle, and this is the black holes are spiraling in. Each wave of that, so each cycle of the wave is half an orbit. So you get one wave, two waves, one wave, two waves. It takes about 10 waves. That's about 5 orbits of these black holes before they merged, and then it rang down to one black hole spinning on its axis. And look at the time. This happened in a fraction of a second, a tiny fraction of a second. If you look at the green line here, this is how fast they were moving. This is measured on the left axis, the velocity in terms of relative to the speed of light. These things ended up moving, if you look over to the right here, at over half the speed of light. So two black holes that went round each other 5 times in a fraction of a second, moving at half the speed of light, and then merged. Now, we can actually determine the properties of these black holes. We determined they were two black holes, one of about 29 solar masses and one of about 36 solar masses. There's a bit of uncertainty on those measurements, but those are the measurements. It happened about 1 billion light years away, so 1,300 million light years away. We determined that fairly quickly from the measurements. The max speed, the final max speed was about 6 hertz, and it ended up in one black hole spinning at about 100 hertz. So one black hole spinning 100 times a second. Very incredible speed. The final black hole was 62 times the mass of the sun, 62 solar masses. This M with a circle dot represents. Now, I don't know how many eagle-eyed mathematicians are in the audience, but those initial masses are 29 and 36 times the mass of the sun. If you add those together, you get 65 solar masses. 65 solar masses of stuff merged into 62 solar masses of stuff. And we've lost 3 solar masses. And that is the energy that went at the equivalent energy, if you convert it into energy using E equals mc squared, that you get that's been emitted in gravitational waves. So the energy it released was 6 times 10 to the 47 joules, which is, if you do E equals mc squared, with M being 3 times the mass of the sun, that's what you get. Now, you do an experiment in your physics laboratory and you get an energy of 3 times 10 to the 47 joules. You've probably done it wrong. But this was the most energetic event ever witnessed by humanity ever. And if you look at the peak power, the peak of that emission, 3 times 10 to the 49 watts. I mean, compare that. The sun is 10 to the 20-something watts, 26 watts, I think. So this is millions and millions of times more power from the sun. And in fact, that peak power, if it had been in the form of, or compared with the light we get from stars, is more power than all the stars and all the galaxies in the entire visible universe combined. Right. So for a brief fraction of a second, this was the most powerful thing going on that we'd ever seen, we'd ever witnessed. And yet all we watched it do here on Earth was move 2 mirrors, tiny fraction, a fraction of the width of a proton. Now, I want to stop and get on to where we are. We've done several things. It wasn't just one event. In the first couple of observing cycles, there were 2 events, lots of events, about 11 events in total. Actually, after 3 observing runs, these are all the different waveforms of the different events. There's now 90 of them. We can also start to pin them down in the sky. By looking at the globe of the sky, we can pin these things down to regions. They're not always very wide. If you only have 2 detectors, this is done essentially by triangulation. Triangulation, the key in the name is having 3 detectors to do it. So with 2 detectors, if you have it first, the 2 LIGO detectors, you don't do very well. You tend to pin it down to a ring on the sky. But with 3 detectors, you tend to pin it down much better. Now, one of those events was really interesting because one of those events, in fact, it was this yellow one on the right here, was pinned down and was seen to be very, very low mass. And instead of being tens of solar masses, it was about 1.5 solar masses per object, which means this probably wasn't a black hole. This is probably neutron stars. So these are the remnants of exploded stars. Often, just as these black holes were, massive stars that come to the end of their lives, but not quite as massive as the ones that form black holes. And these neutron stars would have merged and collided together. But because there's matter there, the stuff, nuclear material, they would have created a flash of light. And indeed, astronomers very, very quickly went and found a flash of light in a galaxy about 120 million light years away from memory. And so we not only got gravitational wave emission that LIGO detectors have found, we got electromagnetic waves, we've got optical light, gamma rays, X-rays, infrared, radio, all sorts of observations of these things that we could go and look at. And why is that important? Well, this was something called a kilonova, so it's slightly less bright than a supernova. And the reason these are important is because the processes that go on in these events when neutron stars merge are thought to create some of the heavier elements in our periodic table. So you've probably seen a periodic table. This is a very colorful one, and the colors say where things are formed. We get things formed in the Big Bang, so hydrogen and helium largely formed in the Big Bang. We get things in dying low mass stars and exploding massive stars. We get formed some of these green bits, and we find stuff formed in stars like the sun, the carbon and the nitrogen and so on that gets sent out through the universe when they die, and some of these heavier elements as well. But this orange stuff is formed when neutron stars merge. And so if you've got, for example, let's find, here's gold, here's silver, palladium is somewhere, so 46 is palladium. My wedding ring is made of palladium. You might have gold jewelry on, a silver jewelry on. That material was formed from 2 neutron stars merging and colliding and creating gravitational waves that would have been detected. And so now we can go and learn an awful lot more about where some of the stuff we see comes from. So, where are we now? We are in the next slide. This is a graphic depicting all the things we've found. So this is each pair of objects merges. These blue objects are the black holes we've detected, different masses, shown as the vertical point on the axis, and the other dots here are the electromagnetic detections of either neutron stars down here, or the red ones are black holes. So we've seen an awful lot. We've seen 90 of these things with gravitational waves, and they're all very, very, very massive. What's the plan for the future? This is this sensitivity plot I showed before, and as the different lower curves are showing how good the instrument will get over the coming upgrades as we go through the next few years. The years are slightly out of date now. It's going to be a little bit later than some of these just because of the pandemic and so on. And so if we look at how many we found, as the detectors have got more sensitive, we've been able to see these things. We saw them once a month for the first couple of observing runs back in 2015 and 17. And then in 2019 and 20, in observing run 3, 2 halves of it, we saw them about twice a week because we were more sensitive. If you're twice as sensitive, you can see these things twice as far away. But space is 3-dimensional. You can see them twice as far away in each of 3 dimensions. So they're 2 times 2 times 2 is 8. So if you're twice as sensitive, you can see these things at 8 times the volume of space. And these things, in the terms of the universe, are happening, uniformly throughout space. And so the prediction is that if you go on to the future, to 2023, so next year when the next observing run starts, and then to the next observing run 5 in 2027, that we're going to be sensitive to much greater distances. So much greater volumes of the universe that we can see these things over. And so instead of finding 2 per week, which is in 03 in the middle here, we might next year be seeing them maybe daily. And then in the final observation, maybe 6 per day. So we have 90 of these things so far. You observe for a year, you see 6 of them per day. Well, that's thousands of these things. So we're going to build a massive catalog of these objects. And we'll pin down how often these black hole mergers tend to happen, and what that tells us about the stars that formed them, and actually can also tell us a little bit about the expansion of the universe and how that's evolved over time as well. So stay tuned. Observing Run 4 begins next year, spring next year. If you want to know a little bit more, then I had a recent trip to the observatory, one of the LIGO observatories. So if you go to the Pythagorean Astronomy podcast, or pythagastro.uk, you can find some episodes there about my trip to LIGO Hanford. You ought to hear a little bit more. So thank you very much. I think there's a little bit of time for questions, but I'm not sure when you have to move on to your next lesson. Thank you.